Hi students, the title of this recording is When Particles Collide, and the main topic is kinetic molecular theory. The subtopics are kinetic molecular theory, KMT, collisions or the rate of collisions, and the effect of variables like temperature and the amount of gas on the rate of collisions of particles. This ties in with one of the questions I have asked you to answer in preparation for your test. In this, we're going to have a lively story about the journey of a tire, a fairly rigid tire. And in this treatment, in this story, it's going to be a bit of a storyboard. I'm going to zoom in on this tire and zoom out to kind of create a feel of perspective, but I really don't want you to think about this tire totally changing shape too much. While it is true that in situations of temperature decreasing and increasing, let me restate that. In situations where the outside air pressure changes, or the particle density, that there would be a change in volume. For the purposes of this story, the volume's not really going to be changing unless I say it's so. I really just want us to focus on the particle collisions inside the tire and what that does to the internal pressure in this tire. So for starts, this tire finds itself one day in the desert, super hot. So it's going out east, and sometimes this tire may find itself in Lake Tahoe, maybe it's going skiing. So as icicles, snowman, it's a great day for that. Another day, this tire finds itself in outer space. And not just even on Earth, it's in the deepest, farthest reaches of space. Or of course, this tire really wouldn't be a tire anymore. It would be exploding because there is the particle density outside this tire is pretty much non-existent. There's no external pressure, so basically the internal pressure in this tire would cause it to explode. But what we are concerned with are what are the gas particles doing inside this tire. Now, when we're looking at this drawing, I kind of want you to think about these trails here, and basically what these trails are related to speed, the distance covered in an interval of time, and when it hits the walls of its container, it is colliding with them. And I'm going to show that by these white hash marks. What I also want you to think about is that these collisions are not really happening between the molecules themselves, the gas particles. We're not thinking about that. We're thinking of the gas particles hitting the walls of the container, and as a result of that would be pressure, and that's what we're talking about. So collisions and the rate of collisions and how that changes the pressure inside this tire. So what happens when you add air? So say you pump some air into this tire. So what happens is, and this is a little reverse, but you start with the left, you have one gas particle making one collision, and now you have, say, 4 gas particles, and now you have 4 times as many collisions. So the more gas particles you add is directly related to the number of collisions or the rate of collisions, and therefore the pressure. So let's talk about a situation, now let's talk about the desert, right? So we have an increase in temperature of the external temperature. So of course what's going to happen is it's going to speed up this molecule. So something I want to point out is this, in particular, that the only thing we can change about these particles really is their speed. Because you really can't really change its shape, and you really aren't going to be changing the potential energy of the system of these particles by rearranging them. So in terms of when you're increasing the temperature, we increase the speed. And as you can see in this drawing, you're increasing the rate of collision. So the collision rate is increasing. So in the same amount of time, there's going to be more collisions with the walls of its container. So what happens in a case where we are reducing the temperature, say it's in Lake Tahoe, well, the molecules or the particles are going to slow down, and you're going to also lower the rate of collisions with the walls of the container, thereby lowering the pressure. And with that, with the fewer collisions, they're also going to be hitting less hard. And if I was to step back a second, when you were looking at when the temperature was increasing, not only would they be hitting more often, they would also be hitting harder. And to go forward back to where we are now, as the particles are moving slower, they're also going to be hitting the walls less hard, in addition to reducing the less frequent. So what happens in the farthest reaches of space where we have a 2.7 Kelvin temperature here, which is pretty low? Well, as you can see, the particle pretty much slows down. It's not even hitting the wall at this point that often. We're talking very, very few collisions. So not only would the pressure decrease and the force they're hitting the wall being a lot less hard, this tire would also practically explode. So we're talking exploding tire, and the gas particle density outside is pretty much non-existent. External pressure is non-existent. So all internal pressure pushing on this tire wall, it would explode. So in addition to the particles not really moving that much, even that little bit that they're moving is enough to make this tire explode. So let's have a note about speed, which I didn't cover before. When I'm talking about the average, when I'm talking about the speed of the system of these gas particles, I'm thinking about an average speed of all of the gas particles in this tire. And to give another way to say that is that I have all these gas particles. They're all moving at different speeds. There's a collection of different speeds. And what they do to get the average is they add up all these speeds and they divide by the number of gas particles to give us the average speed. So when I'm asking you to think about this question, and I say kinetic molecular theory, I want you to think about the rate of the collisions and the effect that temperature and the amount of gas have on the rate of those collisions.